Our second session of the day. We're coming down the home stretch here at the conference, the workshop. Our next speaker is Nathaniel Berestiki, who's going to tell us about what happens to a random walk before equilibrium.
Okay, so thanks very much to the organizers for this kind invitation to speak at this workshop. And so I want to talk about a question which is somehow related to the theme of the workshop, but which I think is also a bit different. And the question is, well, okay, so let me try to say what I have in mind. So Gn will be a sequence of graph, and mostly I'm thinking of the case where these graphs are vertex transitive. And I'm also thinking that the size of this graph is growing with n. And also their degree, which is the same for every vertex, typically will be large. But OK, so that's just a setup. And what I want to say, the question that I want to ask, OK, so we know that if you start running a simple random walk in continuous time on this graph, and you let it run for long enough, then eventually we'll converge to the equilibrium distribution. The question I want to ask is, the title, which is what happens before the equilibrium. What happens to this random walk before it's reached equilibrium? And of course, there are lots of things you could think of looking at. For me, the question that I'll be interested in is the following. So you start the random walk at some specified vertex, let's call it the origin, and you look at the distance of this random walk after a certain time t to the starting point. So the distance is measured in terms of the graph distance. Okay, so the minimal number of edges you have to cross to go back to your starting point. And so at time 0, so this is time t here. At time 0, of course, the distance is here. We know that if you run the Markov chain long enough, then eventually it's going to reach some sort of equilibrium distance, which is the average distance of the graph, delta n, let's say. And the question is, well, what happens here? What happens in between? And so of course, this depends very much on the kind of graph that you're talking about. And in the first example, so ideally, I would like a theory. So far, I have not much more than a collection of examples, but I think the examples are sufficiently interesting that you can ask sort of more general questions. So let me describe a first example, which I think explains why this question might be interesting. So the first example is the case where the random walk is a so-called random transposition random walk. And so the way it works is Gn is a graph whose vertices are the permutations of n objects, n cards, let's say. So this is a symmetric group. And the edges are such that you can move from one permutation to another if you can transpose two elements. And so you put an edge between sigma and sigma prime if sigma can be written as tau times sigma prime, where tau is a transposition. Okay, so if you think about a deck of cards, what it means, if you think about the random walk, you start with a deck in order, and rate 1, continuous time, you choose 2 cards at random, and you switch them, and you look at the permutation that you obtain as time evolves. And so this is a very, of course, well-studied random walk. So first of all, there's this very famous, I hope I'm not getting the spelling wrong, Diaconus of Shah-Shahani.
Yeah, it's Shah-Shahani.
Yeah. There we are. thanks. And so it says that the mixing times is 1/2 n log n. And so what I want to do is look at what happens before equilibrium, as I said. So I'm going to choose a different scaling of time. And sorry? So I'm doing things in continuous time.
Oh.
Yeah. Yeah, so continuous time, yeah. Okay, so here's the first result, which is so it's a result that I proved jointly with Rick Durrett, which appeared in 06 or 07, I don't remember. And the result says the following. So let's look. Let d of xt be the distance after a certain time t. So we have the following convergence. So you look at 1/n times the distance at time t times n. So t is a fixed constant here. Okay, so let's fix a t strictly positive. You look at the distance after a constant of order n number of transpositions, and the distance converges to a certain function, a deterministic function in probability, as n goes to infinity, which has two different expressions. So for t strictly smaller than 1/2, its f of t is just t. But for t greater than 1/2, it has a more complicated expression, which is sum k equals 0 to infinity of 1/2t, k to the k minus 2, factorial k, 2t e to the minus 2t raised to the k. And that's for t greater or equal to 1/2. Okay, so this describes the evolution of the distance as time increases. And if you were to plug this function here, what you would find is a graph that looks like this. So for t greater than, for t smaller than 1/2, it's linear. So this is 1/2 here. But after t equals 1/2, it starts curving down. So this is the maximum distance, which is, well, when you scale things by n, it's 1. And so it starts curving down here. And so this function f is continuous. It's actually C1, but not twice differentiable. And in fact, perhaps if you were to plot something which is more visual, you would want to plot the instantaneous speed, so the derivative of this thing. And the derivative of this thing says that the speed is 1 till you've reached t equals 1/2. And after that, you get this sort of function. This sort of function is very reminiscent to the sort of pictures that appeared in Alain Sokal's talk yesterday, and that's not a coincidence, actually. The phase transition which is going on here is related to the phase transition of the Herder-Schrödinger random graph, which is the percolation phase transition. And so I won't have time to prove this result, but the sort of message here is you've got this sort of natural random walk, and you look at the distance, and it starts evolving. The distance grows as fast as it can for a certain amount of time, and suddenly, after a critical number of transpositions, the distance is still growing, but a lot slower.
Excuse me, I think it must be a typo there. Should the sum be from k equal to 1, or what should it?
Oh, sorry, yes. Yes, thank you. Okay, so as I said, I won't prove this result, but perhaps I'll say a couple of words. So the just a few words about the proof. So the key idea for the proof is, well, in some sense, very, very non-geometric. And it consists in looking at the cycle decomposition of the permutation. So you have a permutation, you can write it in cycles. Some product of cycles like that. And what this means is that this element is mapped to this, and this element is mapped to this, and so on and so on. That element is mapped to that. So this is the orbits under the action of the permutation. And the first fact is that the distance of a permutation to the identity permutation is just n minus number of cycles of the permutation. And so this is an old fact which goes back to Cayley, I think. And the second fact which is used is that if you try to count the number of cycles of this permutation, which is evolving in time, then what you will see is that number of cycles is approximately given by the number of components of an Erdős-Rényi random graph with suitable parameters. So number of cycles at time t is approximately number of components in G and P, where all I have to tell you is what P is, and P is the probability that you have an edge, is the probability that you've made this particular transposition before. So it's it's approximately Tn divided by n choose 2. Well, sorry, if I look at time t, so this is just this. And okay, so let's not look at why this is true. But if you're willing to believe this fact, then you see that when t is when t is of order n over 2, then p is of order 1 over n. So you have indeed the phase transition that I'm talking about. And if you're more interested in why this why you have a relation to the Erdős-Rényi random graph model, it's simply because, in fact, what's going on is that whenever you make a transposition, then two things can happen. So you look at the cycle decomposition, and two things can happen. If you happen to pick two markers in different cycles, then you will observe a coagulation of the cycles. But if you were to pick two markers in the same cycle, then this is going to give rise to a split of this cycle. And so you have this coagulation fragmentation process going on. And somehow, if you forget about fragmentation, what you can see is that this is exactly the Erdős-Rényi random graph model, the dynamical version of the model. And so that's why there is a relation to the that's why there is a relation between the two models. I don't want to go into these details, and I prefer to keep going, and you can ask me more details if you want a different time. Okay, so so that's one type of behavior. There's this phase transition, and I want to describe what is, in some sense, what I think of as being the extreme opposite of this behavior. And this is also a random walk on the permutation group of n cards. And this is the case where the transpositions, just like in Jim Field's example yesterday, are constrained to be adjacent. And what's going to happen here is we're going to find a behavior which is much, much different. So there will be no phase transition, and in fact the distance will be sublinear, meaning at every scale, meaning that there's no phase of time where the distance increases linearly with time. And okay, so formally, what is this? So we have n greater or equal to 1. The transposition that we're allowed to make are the transposition to I, where these are the transposition I minus 1 I, and I have to take I between 2 and n. So in particular, I'm not allowing to transpose the two extreme cards. Okay, so again, let d be the distance. And what do we want? Okay, so what's going to happen is that there will be three different regimes for the evolution of the distance with three different formulae, but there's no point at which you can sort of pinpoint and say, aha, this is where you go from one regime to the other. So let me explain more precisely what I mean. So first of all, mixing time, as we heard in David Wilson's talk, is about n cubed log n. And so I'm going to look at time scales which are smaller than that, but as we will see, it sort of depends on which time scales I'm talking about. So the first time scale is the following. You take, you make of order n adjacent transposition. So let's say that t is some fixed constant s times n, and s is sort of your rescale time variable. Then, okay, so then the theorem says that 1 over n times the distance at this time converges to some deterministic function, which I won't tell you what it is, but I won't tell you what it is, but it's C infinity, and it's sublinear. Actually, at infinity, it behaves like square root of t. F of s is approximately square root, some constant and square root of s for large s. So that's the first regime, and that's when you make that's when you make of order that's when you make of order n steps. So there's a second regime, which is when you make of order n cubed steps. And I prefer to tell you this. There will be a regime in between, but let me tell you about it a bit later. So the third regime is the following. So you make of order n cubed transposition. So you are in some sense close to mixing at that point. So if t is some constant times n cubed, then you can show that 1 over n squared times the distance is converging to a function which I can tell you exactly what it is.
These are all convergence in probability.
In probability, yeah. And I can tell you exactly what this function is. It's the probability that if I start two independent Brownian motion on the unit interval 0, 1, and I make them reflect at the boundaries here, and they're starting uniformly, on the unit interval, it's the probability that at time t their order is reversed. So this is b2 of t, and this is b1 of t. So it's a probability. It's a probability that b2 of t is smaller than b1 of t, where b1, b2 are two independent reflecting Brownian motion on 0, 1. Sorry, S. And so again, this is very continuous, very C infinity function, very diffusive, tends to 1/2 very, very quickly, in fact, and this represents the fact that in some sense the distance has reached its stationary value. So there's a regime in between, which is everything in between. So if t is much greater than n, but it's also much smaller than n cubed, then let's see, what's the distance? I forgot. The distance at this time is what? It's okay. I write it like that. it's approximately f2 of t, which is 1 over n square root 2 over pi times t. And t you imagine is a function growing with n, but it's much bigger than n and much bigger than n and much smaller than n cubed. So again, it's something that has a very diffusive feel to it. And
You won't divide by n?
yeah, so what I claim by this is that you take the ratio of those two things and it converts to 1 in probability.
I don't think you should have 1 over n there, if you compare with case 1 and 3.
Sorry, n.
Yeah.
Thank you. Okay, and so what I want to say is that okay, so you see there are these 3 different regimes, but in some sense, the transition between these regimes is very smooth. I mean, you sort of never see it. There's no time at which you can say, well, you know, for time smaller than this, I use formula 1, and for time greater than this, I use formula 2, and so on. It's sort of all happening asymptotically. In some sense, it's a very opposite behavior to the first case where there was a clear phase transition between 2 different formulae. And just in one word, what's the reason?
Daniel, can you clarify the normalization? When t approaches n cubed, you get there n to
The n should be inside the square root.
Let's see.
that would look much.
Let's see. So that's not what I have, but I might have copied the formula wrong. If the n is within, I agree that this coincides. Yeah, so that's probably what it is. I probably just copied the formula wrong. By the way, these papers are on the web. This is also with Rick Duet, this theorem. This paper is on the web, has just been published in EGP. The first one was in PTRF. Okay, so that's the theorem. Just in one word, what's the reason for this behavior to occur? Well, there's actually a formula for the distance. The distance of a permutation, when you're constrained to use adjacent transpositions, is known to be the number of inversions. So it's the number of times I smaller than j such that sigma I is greater than sigma j. And so, for instance, if you're concerned about the expected distance after time t, then it's a sum. Yes, it's a sum of probability that xt of I is greater than xt of j. So what you have to do is follow the trajectories of given particles I and j. So you look at particles I and j, and so here's 1, here's n, here's I, here's j, and you have to follow their trajectories. And because you're talking about adjacent transposition in continuous time, these particles are performing simple random walk, except that when they're adjacent to each other, then they sort of have to, they cannot occupy the same place. So they're transposed to one another in some sense. So what this comes down to is that these particles are following a trajectory which is just simple exclusion on the interval 1n with reflection at, well, yeah, with reflection at 1n. And so you can see what's going on. Well, for instance, in the third regime, we're really looking at diffusive time scales. And you can use the result of Duret and Claudia Hauser that says that the trajectories, if you rescale that, are going to converge to 2 independent reflecting Brownian motion. Okay, so that's what's going on. So there's the exclusion process sitting underneath, and so you can make all these explicit calculations, and somehow this simplifies things a lot. Okay, so we've analyzed a number of different examples, and it turns out that in some sense, I think these are close to the most two general things that should occur, most reasonable examples. Of course, I have no way of making this conviction precise, but I can tell you what's going on with other examples. And so the examples are like that. So you have, okay, so a trivial case is the case of the hypercube. There is a random walk on a random three regular graph. There's the case of the refill shuffle. So we've analyzed these cases. So first of all, the mixing time. What is the mixing time is? So it mixes in n log n, and there's no phase transition for the distance. So on the on a random three regular graph, which is just a graph chosen uniformly at random among all those that are three regular, then let me not tell you what the mixing time is. There's a phase transition at time 3 log base 2 of n. And what happens is sort of funny. I mean, the distance starts growing exactly linearly, but eventually when it reaches this point, then it stays where it is. And so this is started from a given vertex. And actually, we think that at this stage, after exactly this time, the random walk has mixed. I don't think it's been proved. So of course, this is starting from a given vertex, which is chosen at random, and not starting from the worst possible place. So I'll put a question mark here. So the refill shuffle. Well, the mixing time is 3/2 log base 2 of n. This is a result of David Aldous, famous result of Aldous. And it's kind of interesting. So, by the way, the speed is 1/3 here. So what's going on for this walk is that the walk is it looks like it's walking on a three regular tree, and then eventually it reaches the end of the world, and it mixes and stays there and can't go back. And there's some sort of similar thing which happens for the refill shuffle walk, except that the phase transition happens before the mixing time. And so the phase transition is at time log 2n, and you have a speed 1. And once you've reached that speed, you just stay there, and the mixing time occurs sometime later, somewhere here. It's kind of a bit mysterious, I think. Okay, so general question is, what are the possible things that you could see? What can you say, more generally about random walk? At this point, you would like to have some sort of theory and not just a collection of examples. And it's difficult to say anything. It seems to be a difficult question to say anything. There is one result available which sort of describes the geometry of the phenomenon, which tries to say, well, if you have a random walk that has a phase transition like that, what can you say about how does the geometry have to look like? And it turns out that you can say some things. See, what's going on is really you have the random walk, and at first the degree is very large, so it feels like it's walking on a tree, and so it goes as fast as it can, typically. But after a while, it realizes that it's walking on finite space, and have to slow down. I mean, anyway, it can't go on forever, and so it has to slow down. And it turns out that there's a way you can formulate this intuition. I think, given the time, I'm not going to state the result more precisely. It involves looking at hyperbolic constants of the graph. Okay, so it's fancy vocabulary for a simple idea, I think. Yeah, but the phenomenon is a bit subtle, because it may very well happen that the walk is sort of staying concentrate on a very tiny portion of the space. And so you have to express the fact that suddenly the walk is feeling that the space is becoming less and less hyperbolic in a way that takes into account the fact that it's the geometry of the space as perceived by a random walker. So it's, I'm sorry that I don't have much time to state a precise result here, but this is, in essence, what's going on. So I'd like to end this talk with just giving one example that I think is challenging and interesting, and it's the case. It's still a random walk on a permutation group, and it's the case where well, maybe the best is to talk about transpositions, but I sort of want to interpolate between the totally random case of random transpositions and the case of random adjacent transpositions. So you ask, so you fix L greater than 1, and you can think of L growing with n. And you ask to, at each step, you transpose two markers chosen uniformly at random from those that are spaced no more than L apart. Okay, so so transpose I and j if I minus j is, well, if xt of I minus xt of j is smaller than L. Okay, so and then you make the transposition, and you can think on the cycle perhaps. This is a bit more natural. And okay, so for L equals to 1, this is exactly the model of random adjacent transpositions. For L equals to n, then this is exactly the model of random, fully random transpositions. So you might expect that if L is very large, this should behave a bit like fully random transposition, and if L is very small, this should behave like random adjacent transpositions. So the natural question is, where should the cutoff occur? So for small L's, there's no phase transition, and for big L, there is a phase transition. And I have a conjecture on this and some partial results, which are work in progress with von Peled. And so the belief is that the only thing that should matter is whether L is bounded or not. So if L is bounded, I believe that there is no phase transition. But if L tends to infinity, then there is a phase transition. And I forgot to say that many of these problems, actually, we started studying these questions because of something that arises in computational biology. And this is a case which has practical applications. And okay, I'm going to stop here.
Maybe you can still try and make an effort to state the hyperbolic theorem. Assume that we know all the definitions, or will be motivated by your statement to look them up.
Okay. 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 So what's the statement? So if you look at random transposition, let's say, you fix a constant A. Oh, sorry. And what I want to look at triangles at distance. So this is what I want to do. I want to choose a triangle such that one point is the origin, and x and y are chosen according to the heating distribution, the harmonic measure on the sphere of radius an. Okay, so the harmonic measure means that you're looking at geometry as perceived by the random walk, and I claim that if A is strictly smaller than a quarter, then the triangles are delta thin for some constant of order 1, when for A, so T is delta thin with high probability, And for a greater than a quarter, then when you make the same choice, then the triangles are very fat. So so the hyperbolic constant is of order n.
But you have the general principle that relates this to the phase transition of the random walk.
Okay, so it's no, yes and no. So yeah, I mean, what you can see is that how should I put it? What you can see is that whenever you're in a phase that's not linear, then the hyperbolic constant has to be very big. You expect this to be the case for very simple reasons when you're in a phase that is fully linear, but what I can prove, if you want, in the general case, I can prove that the length of this geodesic is is approximately the same as the sum of the two lengths, and that somehow should imply that you're in a hyperbolic phase. But I need the specific geometry of random transpositions to prove that actually there are some geodesics that stay close to one another.
Okay, next slide.